Alright guys, a little surprise for you, because that's the end of the semester, and of course courses are over, classes are over, so I was thinking probably you're gonna missing me during the coming weeks. So I wanted to do a little something for you in this form of a video, basically. Alright, so of course I'm not going to tell you about my life, because you wouldn't care, but something that probably you would care about is these two things. These two things are, as you can guess, maybe the exam papers from last year, all right, 2015. So what I'm going to do right now in front of you through this camera is just to go through those questions and basically to show you on this board the solutions, at least the solutions that I would expect you to write down in your paper last year if you wanted full marks, if that makes sense. All right, so I have the two papers, 3801, 3901 for the higher version, and I will go through all of these questions right now. So let's start with question number 1 for 3801. So the question says, let x be a number selected totally at random between 0 and n, so 0, 1, 2, up to n, so integers, for some positive integers n. The probability that x takes the value k is just 1 over n plus 1 for all the values of k. This is called a discrete uniform distribution. Yeah, that's a discrete distribution because it can only take the values 0, 1, 2, up to n. Uniform because it assigns basically the same probability to each of those values. So question A, find the expectation of x. All right, so that's question 1 for 3801. All right, question A, it's a very simple question. You can see that it gives 1 mark for it. Of course, the amount, the weight that each sub-question carries should give you an indication about how long and how complicated, so as to speak, the solution should be. Here, 1 mark, you should expect that should be very short and very simple. Indeed, that's the case. Find the expectation of x. Well, x takes all the values between 0 and n with the same probabilities 1 over k. So you know that to find the expectation of a random variable, basically, you have to sum over all the possible values. So here again, everything from 0 to n, the value k times the probability that x would take that value. Alright, so here, because we are given these probabilities, they are all equal, and equal to 1 over n plus 1, you can basically take this outside, the sum, that's 1 over n plus 1, sum of the first k integers. Okay, and you are given a hint in the question. You know that I do like doing things like that to give you hints, basically, to put you right on the right track. The sum of the first n integers is, that's something that you probably know otherwise, this n times n plus 1 over 2. You have this obvious simplification, meaning that the final answer is n plus 2, which makes sense. We are picking basically one number at random between 0 and n on average. You pick the middlemost value, which is n over 2. Alright? Part B now. 2 marks, so that should be slightly longer. Let's say the variance of x. So the variance of x, the easiest way I suppose to obtain something like that is to go through the path of taking the expectation of x squared minus the expectation of x squared, right? And the expectation of x, oh, we do have it, that's n over 2 here, so the expectation of x squared, well, same expression as this one. You sum over all possible values, this value squared up times the probability assigned to it. So that's k squared probability, or write it directly. 1 over n plus 1, because that's the same thing as before. So that's 1 over n plus 1, the sum of the square, this time of the first n integers. And again, I gave you that hint that the sum of the square of the first n integers is that expression there, n times n plus 1 times 2n plus 1 over 6. Okay, so again you have that simplification, I suppose. And that's just n 2n plus 1 divided by 6. Alright? That's the expectation of x squared for the variance. You obtain basically this. one you obtain there. And if you expand this and you simplify what needs to be, you obtain a final value of, look at that, n squared over 12. I write it here for you. N squared over 12 plus n over 6. But see now, suppose that n follows the Poisson distribution, so it's part C here, n follows the Poisson distribution with a certain parameter lambda, and conditionally on n, x is selected totally at random in 0, 1, n. So in fact, that's the same exact distribution as above. The only thing is that now the maximum value n is taken at random according to this distribution. All right. The thing is that precisely if this n is fixed, we do know the expectation and the variance of x in that case because that's parts A and B. All right. If n is fixed, we know everything. Let's pretend for the time being that we know x. Statistically speaking, that means that we will condition on n. All right. So basically, we want the expectation of x. We write that that's the expectation of x if we do know n. That's the law of iterated expectation, right? This thing, we know it. Again, if n is fixed, and this is what we say when we condition on it, then this expectation is just the expectation of x as we obtain it from part A. So that's just n over 2, right? So that's the expectation of a certain constant 1/2 times n. That's that constant times the expectation of n. And do we know the expectation of n? Yes, because n follows the Poisson distribution, so it's just lambda. So it's lambda over 2. Okay. The variance of x, well, same thing. If we fix n, then we can use basically the result that you obtain in part B. So let's pretend we fix n. Let's condition on n. We have a relationship between the variance of x and the variance of x if n is fixed. That's the formula for the conditional variance this time. And we know that it gets as follows. That's the expectation of the variance of x if we know n, plus the variance of the expectation of x if we know n. Okay? So again, you know, this expectation of x given n, that's the one we have here. That's n over 2. So the second part here is n over 2, and this one, well, the variance of x, if n is fixed, that's exactly the expression that we obtained in part B, so that was n squared over 12 plus n over 6. From memory, yes, that's what it is. Okay, so you should take across the expectation of that thing. So expectation of a sum of the expectation, and the constant you can write them out of the expectation, so that's the expectation of x squared divided by 12, plus 1 over 6, the expectation of n, plus the variance of n squared, so for the variance of the constant, which is here, can be written out of it but squared up, so that's 1 over 4 times the variance of n. Alright, do we know this? Yes, that's the variance of the Poisson distribution, so it's lambda as well. Expectation of n is lambda. And do we know the expectation of n squared? Not directly, but if you think about it, yes, you can obtain it very easily. Again, because the variance of n is just the expectation of n squared minus the expectation of n squared up, meaning that this expectation of n squared, that's the variance of n lambda plus the square of the expectation of n lambda squared. Right, so that gives you just this expectation of n squared, which is what you should write here. Right? And so that's basically the variance of x. Again, if you put all the pieces together for this, you would obtain the final answer, which is just lambda over 2 plus lambda squared over 12, which was the final answer that I expected. Alright, so this first question for 301 was about conditioning, so I can have a direct look at the analog question for 3901, also about conditioning. It's also question 1. So the question goes as follows. Coin A gives heads with probability S between 0 and 1, and coin B gives heads with probability T between 0 and 1. Okay. They are thus alternately starting off with coin A. What's the probability that the first head is obtained on coin A? So basically you have two coins, coin A, coin B. You start tossing that first coin, you get head, you're happy, and you stop there. If not, you get tail, I assume it means. You switch to coin B and you toss that one. You get head, you're not happy because you want head on coin A. So you don't want to have head on that one. So your only chance then is to have also tails on that coin B until you move back to coin A, and then you hope to get head again, and so on and so on, until indeed you get the first head. You are happy if you have got that first head on coin A, basically. All right, and so precisely the question is, what is the probability that this will happen? All right, so basically we create three events. It's kind of the first step analysis, as I explained in class. You condition on the first thing that could happen, all right, and you expect that maybe that will bring you back to the initial situation, producing that way an equation that you can solve for the unknown probability. So what does that mean in this context? What could happen in the first toss, and you would like that to happen, you get head, okay? Or you don't. So you get tail for the first toss. But in fact, getting tail for the first toss is not that bad in some sense. Of course, you prefer to have a head there directly, but even if you get a tail for the first toss, you can still get a tail for the second toss on coin B. In such a case, nothing is lost, and you could still get your head on coin A as you want. So in fact, I still have to make it clear what is the outcome of the second toss on coin B. So that could be just head. In such a case, it's lost for you, but I have to create actually a third event here, E3, which is you get tail on the coin A on the first toss, you get tail as well on coin B on the second toss. And as you can see, these three events basically create a partition of the sample space. You are covering that way everything that could ever happen on the first two tosses, coin A and coin B. So that's true that I said, okay, it's kind of a first step analysis, but here the first step is basically made up of the first two tosses. So you may say, yeah, but this one is not about the two first tosses. Yes, it is. You just say, okay, you want head on the first toss. For the second toss, basically, you don't care, in some sense, because you have already obtained what you want. All right? So this, in fact, covers two different things, head or head tails. The only thing is that the second toss, what you would obtain on coin B, then doesn't matter much. In fact, that's what I'm saying, what you would obtain, because in fact, you wouldn't even toss that second coin in that situation. All right, so you have a partition of the sample space. What do you do with a partition of the sample space? You apply the law of total probability. That's the point. So if you define the event A, which is what you want, let's summarize it this way. First head on coin A, then you can write that the probability of A is just the probability of A. But knowing that E1 has occurred, the probability of E1 plus the probability that A occurs if E2 has occurred times the probability of E2 plus the probability that A occurs if E3 has occurred times the probability that E3 has occurred. Just total probability law. Alright? And now, probably that makes the thing much easier for you because if you think about that, these probabilities P1, P2, P3, you know them very well in some sense. PE1 is the probability that you get head on the first trial. So that PE1 here is just S. Yes, we are told that the probability that coin A gives you heads is just S each time you toss it. So that's this S. All right? Leave the room for that one here. Probability that E2 occurs, for E2 you need tails and then heads. All right? What's the probability that you can that you obtain tails on the first toss? It's on coin A. That's the probability that you don't get heads. So that's 1 minus S. and you multiply that one by the probability that you obtain heads on the second toss, which is on coin B, that occurs according to the question with rate T. I can multiply these two probabilities because I'm assuming, of course, that the tosses are independent. If you toss the first coin here and then you toss a second coin like there, probably that there is no link between the outcomes that you would obtain in that situation. Alright, so they're independent, you multiply the probabilities there. Right, again, I leave some room for this one there, plus the probability that you obtain E3, so basically tails and tails, so for the same reasons, it's just 1 minus S, 1 minus T, not probability. Right? So now what about these things? Well, again, I said the idea of that first step analysis is maybe to find yourself in a situation which is very similar, if not identical in terms of the probabilities which are involved to the initial situation. And this is what you have. Suppose that you are seeing this, tails and then tails. Basically, what you would do is to toss on the third trial coin A again. But basically the fact that you have already tried 2 times, 1 time on each coin, basically wouldn't influence the probabilities which are only coming. So basically from that point on, you are exactly back in the initial situation. You have your 2 coins, you start tossing coin A, hoping to obtain your first head on that particular coin. So in fact, if E3 has occurred, and this is what you have there, this probability of A is just the initial probability of A. Really, that's what it is. You are exactly back in the initial situation. Right? For the other 2 cases, it's even simpler. Suppose that E1 has occurred. What's the probability that you obtain your first head on coin A? It must be 1, because precisely E1 tells you that you have obtained heads on first trial on coin A. So that has occurred then. You are sure that A has occurred. If E1 has occurred, we say that E1 implies A, meaning that this probability must be 1. Of course, you have the reverse situation here. If E2 has occurred, you have obtained your first head on the other coin, on coin B, meaning that probability of A in that situation is just 0. Okay? So, of course, this, you forget about it, and you just obtain S plus PA 1 minus S, 1 minus T. This is equal to your PA. You have one equation, a linear equation, one unknown PA. Of course, you can solve it very easily. And the final answer was, I think, here. The final answer, if you really solve it, would be S over S plus T minus S times T. And that's the final answer that I was expecting. Alright, so question 2 for 3801 is about the discrete time Markov chain, and the question essentially gathers hello. John, which is my friend John, you know him, is shooting baskets on the court. Alright, so normally a shot will go in with priority P. However, John feels under pressure when he's in a run of successes, and this decreases his ability, so we can imagine that John gets a bit nervous, something like that. So if he has already scored, let's say, K baskets right now, the probability that the next one will go in will be quite less, like smaller than just the regular P. The question tells you that it would be P over K plus 1. So the higher the value of P, the higher the value of K, the more the pressure he feels, so the lower that probability of the next basket going in. So we can understand it. Alright? So let Xn be the current number of consecutive baskets he has made after the nth shot. Alright? Consecutive baskets. So basically we are recording the length of the run of successes that John is in at the moment. Alright? Of course, we start from x0 is equal to 0. So at the time he starts, he has not yet scored any baskets, of course. And then at any step, either that recorded number of consecutive successes increased by 1, meaning that he has scored that particular trial, okay, that particular shot, or xn move back to 0 because he has missed. So basically, if he misses, the chain of the run of successes is broken, and you start again from scratch meaning from 0 in this recording of the successive successes. All right, so the question is, do you think it's reasonable to model Xn as a Markov chain? Give reasons. So indeed, yes, I think it's very reasonable to model that as a Markov chain, because if you know that currently Xn is in state k, so meaning that John has put in k consecutive trials, k consecutive baskets, that gives you all the information that you need for getting an idea about the probabilities that the chain will move one step further or back to 0. It will move one step further if he scores the next basket. That happens with probability p over k plus 1, and knowing k is enough for that. And of course, it will move back to 0 if he misses. That will happen with probability 1 minus p over k plus 1, and again the value of k is totally enough for getting the values of those probabilities, meaning that the probability that some future events occur only depend on the present, not on the past. The future is dependent on the past. If you know the present, that's the Markov property that makes that whole thing a Markov chain. Okay, so you got basically 2 marks about that. Of course, it's more like a wordy solution for that question, and I would accept like anything which goes along the lines of saying that precisely the future is dependent on the past. If you know the present, the probabilities of this or that do not depend on the past, or things like that. All right, so that was part A. Part B, precisely, we have now convinced ourselves that this is a Markov chain, so let's sketch a diagram describing the behavior of that chain. So that's part B. So you start from state 0, start of the process, let's say. John will score this trial with probability P, meaning that we'll move to state 1 with probability P. He will miss, and will stay in state 0 accordingly to probability with probability 1 minus P. If the chain is currently in state 1, John has scored 1 basket. He feels already a bit under pressure. The probability that he will score the next one will be P divided by K plus 1, K being equal to 1 here. That is just P over 2. Okay, so that decreases his ability, and the probability really that he will score the next one is divided by 2 in that situation. Right? Suppose it still scores that one. We are now in state 2. John has scored 2 consecutive baskets there. The probability that he will score the next one, P divided by K plus 1, K equal to 2, that's P over 3. Okay? Suppose he scores. We are now in state 3. He will score the next one with probability P over 4, and so on and so on. Of course, that chain is infinitely long. You can imagine that if John is very successful, he can, score 10, 20, 50, 200 consecutive baskets, why not? Right. Of course, this probability of moving further and further away will decrease quite quickly to 0, but still, you can imagine that that could happen. There is no upper bound to that chain. But anyway, in state 1, I said, okay, we will move to state 2 with probability P over 2, meaning that we move back to state 0 with probability 1 minus P over 2. If we're in state 2, we'll move to state 3 with probability P over 3, meaning that we move back to state 0, meaning that John misses on that trial with probability 1 minus P over 3. From 3, he would move back to 0 with probability 1 minus P over 4. And of course, all those next states would bring the chain back to state 0 with probabilities 1 minus the one which is written up there. All right, so that's the diagram describing the behavior of the chain. All right, part C. It's a typical question in Markov chain. Find the stationary distribution. I will always ask you to find the stationary distribution of the chain, and of course I will ask you a question related to that stationary distribution. That's this part C. A friend of John arrives at the core and sees him shooting a basket. What's the probability that John is taking this shot without pressure? Okay, that means with a probability of scoring equal to P. Assume that John has started shooting a long time ago, and that element of course makes it clear that what you have to do is to obtain the stationary distribution. John has started shooting a long time ago, the process has started a long time ago, so the chain is somewhere here, okay? But it's no more influenced by the fact that we started in state 0. So it can be anywhere according to a certain probability distribution, which is, as you know, the stationary distribution. So we should identify that probability, that stationary probability distribution. All right. So I suppose that the first thing to do for obtaining that stationary distribution is to write down the one step ahead transition probability matrix, capital P here, which is the probability of moving from one state to another one. Okay, so from state 0, you will stay there with probability 1 minus P. You will move to state 1 with probability P. Of course, you cannot move directly further away, so all these probabilities of jumping directly to the higher state, they're all 0. Okay? From state 1, you will move back to state 0 with this probability 1 minus P over 2. You cannot stay in state 1, but you can move to state 2 with probability P over 2. And of course, the remaining probabilities, they are all 0. From state 2, you go to state 0 with probability 1 minus P over 3. You cannot move to state 1. You cannot stay in state 2. You can go to state 3 with probability P over 3. All the other probabilities are equal to 0, and you see that that chain has a structure. On the diagonal here, you have all zeros, you have all zeros here, all zeros there, all zeros here, and here you have, shouldn't do that, non-zero probabilities, and here you have non-zeros probabilities, but that's it. Okay, so you have a very particular structure for this chain. That will allow you to solve very easily the system of equations of which the stationary distribution is known to be the solution. Okay, you know that the stationary distribution pi is obtained as the solution of this system. Pi is equal to pi over pi times p. The only thing is, it's not the only equation that you should consider. You know that you should also force the sum of all the probabilities to be equal to 1, because it's a probability distribution. Meaning that in this system of equation, there is one which is redundant, that you don't need. Okay? In fact, you know that if you sum the elements row after row in this matrix, you always get 1. You can check that very easily. Okay? Meaning that this matrix is not a full rank, meaning that this system, as it is now, is not a unique solution. Okay? So basically, you can just get rid of one of the equation and replace it by the fact that you want the sum of all the probabilities to be equal to 1. Essentially, you can forget about any one of the equations in this system. But there are probably smarter things to do than others. What do I mean by this? If you consider the first row, first column equation that would appear in this system here, you would have to consider this first column. This first column is made up of only non-zero elements. So you have basically to consider all the terms of that big equations. Probably not the right thing to do here, because if you compare the other columns, all the elements are zeros except 1. So that gives you very simple equations. So it's probably a better idea just to look at this part of the matrix, and that equation that would come from the first column, that would be the one which is redundant, that you would just leave aside. Okay, nice thing. So that gives you that pi 1, if I consider here, first line, second column, the second column is the one related to pi 1. Pi 1 is equal to, or you sum pi 0 times this, p times pi 0, plus, well, 0 times pi 1, 0 times pi 2, 0 times pi 3, and so on and so on. That 0, you can forget about that. Okay, so that's your first equation. For the second column, that would give you pi 2. Pi 2 is equal to this, so pi 0 times 0, forget about that, p over 2 times pi 1. For the third column here, pi 3, 0 times pi 0, 0 times pi 1, p over 3 times pi 2. Okay, and I could continue that way, and again you see that you have that quite obvious structure which appears in your equations, and I can solve this very easily. So pi 1 is equal to p times pi 0, fine. Pi 2, p over 2 pi 1, the pi 1 itself is p times pi 0, so it's pi squared over 2 pi 0. Pi 3 is p over 3 pi 2, meaning that because pi 2 is this, pi 3 divided by 6. 6, please allow me to write it as the factorial of 3. Okay. And, well, if you are not yet convinced, you can write a couple more of equations like this, but I suppose that you can believe me if I tell you that pi n is just p over n over the factorial of n times pi 0. Okay, so that's essentially your stationary distribution. Okay, the only thing is that all these probabilities still depend on your unknown pi 0. How will you identify that pi 0? Again, we will force all these values to sum to 1. Okay, so let's do that here. By definition, the stationary distribution is such that if you sum all the values of the pi n's, that's μ1. Okay, so here, the pi n, you have the equation there. Sum for n between 0 and infinity, p to the power n factorial. Pi 0, but pi 0 does not depend on n, it's a constant, so I can write it in front of everything. It must be 1. Do you know what this sum is? You do, because I am writing on for you on the exam sheet. The sum of a certain thing to a certain power divided by the factor of that power happens to be one of the definitions of the exponential function. So this is, in fact, just the exponential of the thing which is there, which is just p. If pi 0 times the exponential of p must be 1, you obtain that pi 0 must be the exponential of minus p. Okay? And in fact, if you read again the question, what is the probability that John is taking this shot without pressure? The only situation in which John will be shooting without pressure is precisely if we are in this state. The friend of John arrives at the court and he finds the process in that state. That's the only situation in which he would see John just shooting without pressure. So in fact, this is the probability that we were after. Pi 0, the probability that that friend of John will see him shooting without pressure is the exponential minus p. Alright, so that question too about the discrete time Markov chain for 3901 was exactly the same as the question 2 for 3801. Indeed, you have seen in the previous papers that I posted that they are common questions. That must be the case. That basically allows me to scale up or down the result for the two versions of the courses. So that, to be fair, okay, if I compare the result of the students 3901 versus 3801 on the same questions, I can tell, okay, those students deserve their marks to be a bit scaled up or not. This is how it works. I tell you my little secrets. But anyway, let's move directly to question 3 for 3801. So it's about the branching process. Okay, so by the end of their life, each individual in the population will have a random number y of offspring with the probability that y is 0 equal to x, the probability that y is equal to 1 is equal to y, and the probability that y is equal to 2 equal to z, of course. X plus y plus z must be equal to 1 because you are covering there all the possibilities. So each individual can only have either 0 or 1 or 2 kids, basically, but that's it. All right. Let xn denote the number of individuals in generation n of the population and assume x0 is equal to 1. So that's really the classical setup for the branching process. All right. Part A. What is the probability that the population is extinct at the second generation? That is, probability that x2 is equal to 0. Okay, if x2 is equal to 0, that means no more individuals in the population at generation 2, and the population is extinct. So that's indeed what the question is about. All right. Well, in fact, there is an easy way to answer this question. and it is basically based on the probability generating function of the random variable x2. In fact, it's always true that for any random variable taking value only on the integral numbers, positive integral numbers, non-negative, I should say, integral numbers, the probability that x is equal to 0 is just equal to that PGF, probability generating function, at 0. This is one of the properties of the PGF that I talked about in class that appears on slide 291. Okay, may have a look at it. So that means that here, if I can identify, let's call it G2, the PDF of x2, then I just to find it at 0, and that would give me this probability. Do I know the PGF of x2 in this branching process situation? Yes, I do, because we know that x2 is essentially a compound random variable. If you look back at the so-called Galton-Watson definition of the branching process, x2 is equal to the sum for k between 0 and x1, so the size of the population in the previous generation, of the y and k. All right? So that means it's a compound random variable, and we know that the PGF of compound random variable is, as its name, the compound of the two PGFs. So here, that would be g at 0, and again, this appears on slide 302, if you don't believe me. Okay? So this is what I need. All right? Do I know G? Well, not yet. G is the PGF of the offspring distribution. All right? But we know that G of S basically is the expectation of S to the power y. So you sum over all the possible values of y. Here we have 3 of them. S to the power k. So k between 0 and 2. Probability that y takes the value k. And I suppose you can trust me that this is just x plus ys plus z times s squared. Okay? So that's your PGF. So g of g at 0, simple. You take s equal to 0 here. This, of course, just goes away. It remains x. So your g of 0 here is x. So that's just g of x. And so you plug x into this expression, like for s. That is x plus yx plus z x squared. And that's exactly the probability that we are after, probability that x2 is equal to 0. And in fact, in this simple situation, we can understand this expression, because what do you need for that population to go extinct by generation 2? Either the first guy, starting from one guy, that guy has no kids. If that guy has no kid, of course the population is extinct by definition. That happens with probability x, this x. Or that guy has one kid, that happens with probability y, this y, and that kid has no kid. If that only kid has no kid, indeed by generation 2, population is extinct. That kid will have no kid with probability x. So in fact, that path to extinction, so as to speak, the first individual has one kid, that kid has no kid, has probability y times x. And finally, maybe the first guy may have 2 kids, that happens with probability z, and the 2 kids, none of them have offsprings, meaning that this happens with probability x squared. So this other path to extinction is as probability z times x squared. Right? So altogether, this is the probability that the population is extinct by the second generation. Okay? Alright, so part B, the question is, find the probability of eventual extinction of the population. And I suppose that's a very classical question. about the branching process. So what is the probability of extinction of the population? So of course, you know that this is what I usually denote in that framework by 0. Okay, probability of eventual extinction for this population. Okay. How would you find that thing? Well, we know that in fact, phi 0 by definition is a root of the equation gs is equal to s. Alright? So basically this is how you should find pi 0. So gs is here this expression, so you need x plus y s plus z s squared equal to z. That's the equation you should solve for obtaining pi 0. You can send that s to the other side. Okay, you have this, and so that's a quadratic equation s that you should solve. You may apply the usual theory for solving quadratic equation, but remember that I said in class, you know one of the roots of that equation, quadratic or not, by the way. You know a root of this equation in all cases. S equal to 1 is always a root of that equation, meaning that in this case, you must be able to write it as s minus 1. S is a root of the equation times another thing. And in this simple situation of a quadratic equation, it's very obvious what you should write there to reconstruct this equation. Alright, so the coefficient of s squared here is z. So because you have s here, that must be here s times z. Okay, minus, well, the independent term here is x. So minus 1 times what you have here must give you x. That must be minus x. If you expand this product, you should find back this equation there. So you may say maybe at first sight, it's not possible because this is y, and there is no y in this expression. Oh, there is one y, it's just hiding. Hiding in what? Hiding in the fact that here, that's here, x plus y plus z is equal to 1. So actually your y is 1 minus x minus z. If you plug that y value here instead of what you have there, you will indeed see that it's exactly equal to that. It must be the case anyway. Okay? So this is the equation that you have to solve, and then I suppose you will agree that it's very simple. Two solutions for this, either is equal to 1 or zs minus x is equal to 0, meaning that s is equal to x over z. Alright? So two candidates basically for being your probability of extinction. What is the right one? Ah, that's the trick. Pi 0 is a root of this equation, but it's not like any root. It is, according to the theory, the smallest positive root of the equation. What is the smallest positive root? Well, first thing, they are both positives. Yes, we can believe that. X and Z, they are probabilities, so of course they are positive number. So it's all about, you know, picking the smallest one. So if x over z is smaller than 1, this one is the smallest, or at least it's equal to 1, meaning that pi 0 is equal to x over z. If x over z is larger than 1, then pi 0 is just 1. That's the final answer. That's the probability of extinction, like the two cases separately. Okay? You may probably recognize that this is the question about the branching process that was asked at the mid-session test this year. True? And that's true that some students just came up with this final answer. Pi 0 is equal to x over z. And we're happy with that. It's not really the correct answer. Of course, if you just write this, you get some credits. But the question here was worth 5 marks. If you just write this and you obtain that correctly, you would probably obtain 4 over 5. But you cannot get full marks because it's not the correct answer. The correct answer is the whole thing. Imagine that x over z is larger than 1. There is no reason why that couldn't be the case. You may have here probability higher than that one. Why not? You would say that pi 0 probability of extinction would be something greater than 1, which doesn't make sense. So that cannot be correct just alone. You have really to give the full package if you want the full credits, which I suppose makes sense. All right. Very quickly, you can do it here. Part C. After 10 generations, the population consists of 3 individuals. What is now the probability of eventual extinction of the population? So you are told that x10 is equal to 3. What is now the probability of eventual extinction of the population? Importantly, if I tell you this, that tells you like the present state of the branching process. Currently, there are 3 individuals in the population. Okay? That's the present situation. Each of them may have kids. Each of those kids may have kids. And so on and so on. So if you want that population, like knowing that now there are 3 individuals in it, you need basically these 3 branches to go extinct. Each of these branches basically will behave like the initial branch that you had and will go extinct with probability by 0. Okay? You need that one to go extinct, and this one, and that one. Each individual will behave independently of the others by the assumptions of the branching process, meaning that the probability of extinction for that situation, starting from these 3 guys, will be just that pi 0 to the power 3, pi 0 being either x over z, if x over z is smaller than 1, or 1, in such a case it's equal to 1 here. Okay? The important thing here is that in fact, the fact that you have here 3 individuals after 10 generations, that 10 doesn't matter at all. Okay? The thing is that if at any time you have 3 individuals in the population, those 3 individuals will like basically behave as any others at any other time, and that's it. That gives you the same probability of extinction. Alright, so in fact this is just a kind of irrelevant piece of information. Okay. Alright, so let's move directly to question 3 for 3901. So it's also about the branching process, so that's the analog question. The question essentially is the same, as exactly the same structure. The only thing which is different is that the probability of spring is a bit more complicated, let's say. So we are told here that we have a kind of bacterium such that every minute each bacterium gives rise to offspring and then dies, or just dies without offspring. The offspring distribution for all bacteria of that kind is the one given here. So the probability that the number of offspring is equal to k is 1 over m plus 1 times m over m plus 1 to the power k, 0, 1, 2, and so on, up to plus infinity, I suppose, for some integer m larger than 1. Okay? A culture of that type of bacteria starts at time 0 from 1 individual. So again, we are told that x0 is 1. It's assumed that all the bacteria in that culture will always behave independently of one another, which is the classical assumption in a branching process situation. Part A, find the probability that the population of bacteria is extinct by the end of the second minute. So again, because here we are told that the bacteria develop like minute after minute. Each and every minute something happens. The bacteria give rise to offspring or just dies. Basically, yeah, a generation is a minute. So we are told here to find the probability that the population is extinct by the end of the second minute. Of course, that means that we want the probability of the population to be extinct by the second generation. Same thing, and I explained in the 3801 solution of that question that is just G2 at 0, G2 being the PGF of x2, and I also said that is G of 0, G being the PGF of the offspring distribution. So I will first find that PGF here. So expectation of S to the power Y, you sum over all the possible values. Here k between 0 and infinity, s to the power k, probability that y takes the value k, which is this. Okay? You have to play a bit with this expression, in particular this 1 over n plus 1, you can write it outside this expectation. This expression now, sum for k between 0 and infinity, Sm over m plus 1 to the power k. Okay. Can you handle this expression? That's the sum of all the kth power of something. And that thing happens to be smaller than 1. Okay? Yes, it's smaller than 1 because m is smaller than n plus 1. And you multiply it by s, and we know that the domain of a definition of that PGF is between 0 and 1, basically. That's the interesting part of the function, at least. So you can always assume in this framework that s is somewhere between 0 and 1. So if s is between 0 and 1, and you multiply it by something which is itself smaller than 1, what you obtain is, of course, something smaller than 1. Meaning that you can use the result that I kindly give you in the statement of the question. The sum of all the powers of x is equal to 1 over 1 minus x if x is smaller than 1 in absolute value, which is the case here. So this is just, well, up to this coefficient, 1 over n plus 1, 1 over 1 minus the whole thing here. Okay? And if you multiply this, you will see that it's just 1 over n plus 1 minus Sm. So this function is the PGF of this offspring distribution. And that's the function g, of course, that you should use. Here, again, g of 0, that bit here, you replace s by 0, this gas, that's just 1 over n plus 1. G at 1 over n plus 1, well, you revise by this. 1 over n plus 1 minus s, so n plus 1 times n. Okay, so this is what you obtain here. And yeah, if you want a better looking expression, you can probably work a bit on it. You would see that at the end, this is equal to n plus 1, n squared plus n plus 1. Okay. So that's the probability that the population of bacteria here will be extinct by the second generation. So part B, find the eventual extinction probability of the population. So again, I said it for the question for 3801, okay, pi 0 is root of gs equal to s. So that means use this expression here. You want 1 over n plus 1 minus Sm to be equal to s. If you multiply everything by this denominator, 1 is equal to ms plus s minus s squared m, or let's write it this way, ms squared plus, minus n plus 1 s plus 1 equal to 0. So that's the equation you should solve for finding the value pi naught, probability of eventual extinction. Again, don't waste your time, solving this quadratic equation using sometimes quite intricate rules of algebra, but take advantage of the fact that you know that in any case s equal to 1 is a root, so you must be able to write this as s minus 1 times something. You have just to identify the coefficient here. The coefficient of s squared must be m, so here you must have an s, the last one there, plus 1 multiplied by minus 1. This one must be minus 1. And so again, you recover the two roots, okay, s is equal to 1 or s is equal to 1 over m. And you have to pick for pi 0 the smallest positive roots. Okay? Because those values are positive, but because m here is taken as an integer greater than or equal to 1, this 1 over n, of course, is always smaller than 1. At the very most, it's equal to 1. But, of course, this is the root that we should pick, meaning that in that situation, pi 0 is 1. Okay? And part C, you know, after 10 minutes, you observe that the population consists of 3 bacteria. What is now the probability that the entire culture will eventually die out entirely? Same thing, you know, you have 3 individuals, you want each branch to go extinct. Each branch will go extinct with this probability. So for part C, you are just pi naught to the power 3, which in this case I can make explicit. 1 over n to the power 3 was the final answer that I was expecting for that question. Alright, so let's quickly move to question 4. For 3801, now we enter the land of exponential distributions and continuous time Markov chains and things like that. So the question is, a system consists of 2 machines and 2 repairmen. Each machine can work until failure at an exponentially distributed random time with mean 5 hours. A failed machine can be repaired only by a single repairman within an exponentially distributed random time with mean 4 hours. Define xt, the number of working machines at time t, and see that xt is a continuous time Markov chain. Of course, I'm telling you here explicitly xt, the number of working machines at any time t, is a Markov chain, but of course you could have guessed that yourself. What is the element that really makes that whole thing a continuous time Markov chain? All the times which are involved, the times that the machines are working before breaking down, and the time needed for repairing those machines when they are down, they are all exponentially distributed. So that's the element. Exponential distribution for the times means that they are memoryless, means that the Markov property will apply. All right. So part A, give the generator matrix of the chain. So yeah, before that, I suppose that sketching the diagram describing the behavior of the chain would be quite useful. So there are 2 machines. We are counting here with xt the number of machines working at any time. So because at most 2 machines, the number of machines working must be either 0 or 1 or 2. Can it be something else? All right, so you have in fact just 3 states for this chain, 0, 1, 2. So if we are currently in state 0, that means that there are currently no machines working. They are both being repaired. Okay? So in fact, both being repaired, meaning that the rate at which you will see one machine going back alive will be 2 times the rate at which one machine is repaired. So you can imagine you have your 2 working repairmen working at the same time on the 2 machines. And the first time that you will see one of the 2 done with that particular repair, you will see one machine back at work, basically. So the rate at which the chain will jump from state 0 back to state 1, one machine is working, 2 times the repaired rate. And basically that's 2 times 0.5, sorry, 2 times 0.25, which is 0.5. Why 0.25? Because we are told that the time that it takes to repair one machine is exponential with mean 4 hours. So indeed, in 1 hour, on average, we will repair 1 over 4 or 0.25 machines. All right. So mu, in some sense, here the repair rate is 0.25. 2 times here, 0.5. All right. Precisely, if we are in state 1, one machine is working, meaning that 1 is still being repaired. Okay, that repair will be done after an exponentially distributed time of rate 0.25 for the reason that I just explained. All right, so in fact, that machine will be back at work with rate 0.25. Okay, but of course, when we are in state 1, there is one machine working. So I said one machine being repaired, that one can get repaired, but the machine which is working can also break again down before the one being repaired is in working conditions again. Okay? So that one will fail with a rate which is the exponential rate of failure, and we are told that that failure time occurs after an exponentially distributed random time with mean 5 hours. So on average, one machine will fail with a rate 1/5, which is 0.2 times per hour. Okay? So that machine will fail with a rate 0.2. Okay? Of course, if that machine fails, we are back in state 0. No machine is working at that time. Okay? So when you're in state 1, in fact, two things can happen. It's kind of a race, as I explained in class. Either the machine being repaired will be repaired before the other one fails down, or that one will break down before the machine being repaired at that time is back on working condition. Okay? If you're in state 2, oh, that's fine. The two machines are working, and they are working at the same time. So nothing being repaired at that time. You can only go on one unit when one of the two machines fail, and that will happen with rate 0.4. Again, the rate at which one machine will fail is 0.2 per hour. If you have two machines working, each of the two can fail basically at any time. So in fact, you will see one machine failing at the minimum time between two exponential random variables, and that is known to have also the exponential distribution, with the rate being the sum of the two, 0.4. Okay, so that's basically the description of that continuous Markov chain, which make it obvious what is the generator matrix of that chain. We know that for the generator matrix of a continuous Markov chain, we have here on the diagonal elements the global rate out of a state. So what's the global rate out of state 0? You can always, or you can, only exit state 0 through that way to state 1. This occurs with rate 0.5. So that's minus 0.5 here. And of course, you can only go to state 1 with that rate. So the rate at which the chain will jump from state 0 to state 1, 0.5, cannot go directly to state 2. Okay? If you're in state 1, the diagonal element is, again, the global rate out of state 1. But you can go out state 1 this way or that way. So the global rate is the sum of these two. So that's minus 0.45. Okay. You can go to state 2 with rate 0.25. You can go to state 0 with rate 0.2. Okay. And we are in state 2. The only way out is this way with rate 0.4, so this is negative 0.4, and you can only go back to state 1, 0.4, 0 is the rate directly from state 2 to state 0. So that's the generator matrix of the chain. Okay. Part B, find the stationary distribution of that chain. We know that for the continuous time, the stationary distribution is the solution of this pi j equal to 0 system of equations. Okay, so you can write explicitly the equations. Pi 0, pi 1, pi 2 times each of these columns should give you, like the system of equation should give you the stationary distribution. So if you write first row, first column here, minus 0.5 pi 0 plus 0.2 pi 1 is equal to 0. Okay, if you write first row, second column here, 0.5 by 0. Oh, you know what? You know that we'll have to skip one of these equations because one is redundant, and again we'll force pi 0 plus pi 1 plus pi 2 to be equal to 1 at the end. Just basically get rid of the most complicated equation. Yeah, it's probably a good idea to do that. So basically this one, you know, you have the three terms appearing in the statement of the equation. So probably that's the most complicated one because for the other two you have 0 giving you a simpler expression. So let's skip that equation. Let's focus on the last one, which says basically that 0.25 pi 1 minus
0.4 pi 2 is equal to 0. Okay? That tells you that pi 1 is basically, if you send this to the other side and you divide by 0.2, you will have 5 over 2 pi 0. And in this one, you have that pi 2 is, send it to the other side, you divide by 0.4, 0.25 divided by 0.4, that's 5 over 8. Pi 1. But pi 1, you know what it is in terms of pi 0. So we replace pi 1 by 5 over 2 pi 0, you will have times 5 over 2 pi 0, which is 25 over 16 pi 0. And now how do you identify the last bit? Pi 0, precisely because you want pi 0 plus pi 1 plus pi 2 to be equal to 1. Pi 0, 1 plus, for pi 1 you have 5 over 2 here, plus pi 2 you have 25 over 16 there, must be equal to 1. If you calculate this with your UNSW approved calculator, that means that it's equal to 81 divided by something by 16. Yeah, that's 16, of course. All right. So 81 divided by 16 times pi 0 must be equal to 1. Pi 0, thank you, is 16 over 81. Pi 1 is this 16 over 81 times 5 over 2, and you will see that it's 40 over 81. And pi 2 is basically 25 over 16 times this. You see it's 25 over 81. Okay? An easy check that what you are saying is not total crap. This plus that plus this must be equal to 1. You can check it indeed. That's the case. Right? So that's the stationary distribution of the chain, part B. In the long run, what is the average number of working machines? Okay, so that's part C. And I have probably enough room to do it here because it's very simple. In the long run, what is the average? It's a long run average. And we know that by the ergodic theorem, a long run average of a Markov chain basically is just the average against the stationary distribution. So that's the expectation calculated from the stationary probability base. All right. So basically, if I call x the number of machines working, okay, the expectation of x will be 0 times the probability that there are 0 machines working. In the long term, that's pi 0. But anyway, 0 times pi 0, I don't write it. Plus 1 time the probability that in the long term there is 1 machine working. That's my pi 1. Plus 2 times the probability that in the long run again there are 2 machines working. That's your pi 2, so 2 times 25 over 81. Final answer. I think 1.11, in fact it's 10 over 9. Okay. And I will not even write it because there are that last sub-question. Given that the working machine can produce 100 units every hour, how many units can the system produce per hour in the long term? So if each machine working produces 100 units, what you produce altogether, that's 100 times x. Expectation of 100 times x, that's 100, constant outside, times the expectation of x. So that's 100 times this number. So in fact, it's 111 units that you will produce. Okay. All right, so I'm gonna skip for the time being question 4 for 3901 because the analog of question 4, 3801, the machines working, is actually question 5 for 3901. So I suppose it makes sense just to have a look first at that question number 5. look back at question 4 right after this. All right, so question 5 for 3901. Again, there are two machines, one of which is used as a spare. A working machine will function for an exponential time with rate lambda and will then fail. Upon failure, it's immediately replaced by another machine, if that one is in working order, and it goes to the repair facility. The repair facility consists in one single person who takes an exponential time with rate mu to repair a failed machine. At the repair facility, the newly failed machine enters service if the repair person is free. If the repair person is busy, it waits until the other machine is fixed. At that time, the newly repaired machine is put in service and repairs begins on the other one. Okay? So, quite a complex situation maybe. So again, I suppose it makes sense just to have a sketch of a diagram here just to better understand what's exactly going on. In fact, it's not that complicated if you really read again all the steps in the question. So indeed, xt, I will write the number of machines down at time t. You can define basically the chain as you want. If you want to define the number of working machines, that's fine. First, there are two machines here, so the number of machines down at any times is just 2 minus the number of machines working and vice versa. So the way you define the chain doesn't matter much, but here in the question, question A, okay, say it again. So of course you define the chain as you want, like you may define xt as being the number of working machines at time t, but that would be exactly the same. There are two machines altogether, so the number of machines down at any time, that's 2 minus the number of machines working at that time, and vice versa. So basically that's exactly the same thing to define the number of machines working or the number of machines being repaired. It's equivalent, basically. Of course, you have to stick to your notation. If you call xt the number of working machines, that will be the number of working machines until the end. All right, that's understood. All right. So we know that we start from 0 machines down because at the beginning of the process, the 2 machines are in working order. Right? And from that state 0, there is one machine working. We said that the other one is not working at the same time. It's used as a spare. So if that one machine which is currently working fails, then the other one then is put in use. But basically it's not working. All right? So only one machine is working at a time. Same thing basically at the repair facility. There is one repairman is working on one machine. Okay? And if it happens that the second machine is also broken at any time, while that guy is still working on the first machine, he will just continue working on the machine he was busy with, and he will take care of the other one after he's done with the first one. So there are no 2 repairmen working on 2 machines at the same time. Basically, there is only one machine being repaired at a time, even if there is one waiting, in some sense. So, if there are 0 machines down, both machines are in working order, but only one is working. So basically it will fail with a rate which is lambda, because we are told that a machine working will function for an exponential time with rate lambda and then fail. Okay, so the rate of failure is lambda. One machine working, even if 2 are in working conditions, but one machine effectively working, so that will happen with rate lambda. In such a case, we have one machine down. If we have one machine down, the other one, the spare one, is being put in use, start working. And of course, that working machine can itself fail at some point, which is also exponentially distributed with a rate of lambda. So we would also move to state 2. With rate lambda, one machine working. But if there is one machine working, that means there is one machine down. Indeed, that machine which is down is being repaired. The repairman is doing pretty good job And you could manage to repair that machine after an exponentially distributed time with rate mu. So we will move back to the initial situation, 0 machines down, so both machines in working conditions, with rate mu. Okay? So when you're in state 1, again, there are 2 things that could happen. Either the chain would jump to the right-hand side, or it would jump back to the left-hand side. Okay? If you're in state 2, the 2 machines are down, but again, there is a 1 repairman who can work only on 1 machine at a time, so the time it will take to repair that 1 machine to move back to state 1 is just an exponential time with rate mu. So this is basically the chain that you have, all right, given the information that we have in this question. Okay, so part A, and see that part A carries 10 marks. That must be quite solid question, that one, isn't it? Okay. Starting with both machines in working condition, find the expected value of the time until both are in repair facility. So indeed, we start with both machines in working condition, so we start from here. This is what we wrote there, x0 is 0. What is the time that we need to find the 2 machines in the repair facility? Okay, so essentially in terms of the Markov chain, what is, on average, the time it would take the chain for moving from here to there? Okay, that's what I call T, total time for making it from 0 to 2, and I can say that it's Q0 plus Q1. Okay, and what do I call Q0? Q0 time it takes for moving from 0 to 1. Okay, so in fact, for moving from here to there, first thing, I need some time for moving from here to there. And then I will take some extra time for moving from 1 to 2, and of course that's the time here that I call Q1. Okay, so that's time it takes for moving from 1 to 2. Okay, so T is Q0 plus Q1. I want the expectation of T because I want the average time that it would take for moving from 0 to 2. I want the expectation of this, so expectation of a sum, that's the sum of the expectation, so I can write this directly, of course. Alright, so one thing at a time. What is the expectation of Q0? It's easy. Why is that easy? Well, because we are in a continuous time Markov chain. Okay? The time we will stay there in state 0 before leaving it is exponential. We know that. With a rate which is essentially the total rate out of state 0. But here there is only one way out of state 0, which is an exponential rate of lambda. So basically Q0 here, I can tell you, write it here, that is just exponential with rate lambda. Okay, because this is the time it will stay here before leaving that state to state 1 in that situation. So Q0 follows the exponential distribution with rate lambda. By definition, its expectation is just 1 over lambda. Okay, slightly more complicated for Q1 because Q1 essentially that's the time you would need to make it from state 1 to state 2. And as you can see for Q1 here we have 2 options. Either the chain jumps to state 2 directly, in such a case it's done, we have achieved state 2, okay. Or it moves back to state 0 and then we are back at the initial situation, meaning we'll need some time for making it back to state 1 and then for maybe making it to state 2. Okay, so Q1 in fact it depends on what is the first transition. It depends on the first transition. Okay, let's condition on that, on the first transition. So I can write that the expectation of Q1 is the expectation of Q1 if the first transition is to the left, and I suppose you're familiar with this type of notation. When I say given left, that means okay, the first transition is to the left, you move back from 1 to 0, times the probability that indeed it gets to the left, times, plus the expectation of Q1 if the first transition is to the right, times the probability that that first transition is indeed to the right. Do I know these probabilities? Probability of moving to the left, probability of moving to the right. Yes, I do, because, and this is something that you can find in the lecture notes on slide 441, actually. You are in state 1. You have here basically a race, a competition between two exponential random times. Okay? And you will move to state 2 if this random time is shorter than that one. What's the probability that among two exponential random times, one is the smallest? That's the ratio of this rate to the sum of all the rates in competition, so as to speak. So, probability that you are moving to the right, that should be just lambda over mu plus lambda, and accordingly the probability that you move to the left is the other one, mu over lambda plus mu. Okay, so you know that. Okay? If you know that the first transition is indeed to the right, what is the time that you need for making it from here to there? Oh, that's done. If you move to the right, you know you achieve your state 2 thing. You're happy? That's over. So basically, if you know that the first transition is to the right, the time it takes is just the time that you spend here in that state 1. And the time you spend there in that state 1 is in fact exponentially distributed, because again we are in a continuous time Markov chain, with a rate which is just the total rate outside of state 1, which is here lambda plus mu. So the total time you would spend in state 1 on that particular visit is on average 1 over lambda plus mu, whatever the transitions to the right or to the left. But knowing that the first transition is to the right just tells you that it's over after that. Okay? So basically, this is just 1 over lambda plus mu. Okay? And the only thing which is slightly more difficult to obtain is the expectation of Q1, but if you know that the first transition is to the left. No, in fact, it's not that complicated, because the expectation of Q1 if the first transition is to the left is what? Well, first thing, the time you spend in state 1 once you arrive. And that, I just say, is 1 over lambda plus mu on average. But now, you are told that you are moving, in fact, to the left. So that means that you find yourself in that state. And so you need some extra time here, which is the time you would need effectively, because what you want really, your total time here, t, is the time you need to make it to state 2. So basically, you need the time you have, you need to make it from state 0 to state 2. But in fact, yeah, that's the initial time. Okay, so that's basically your t again. All right? And we know that your t on average will be the sum of this and that. Okay, so this expectation of Q0 is 1 over lambda. And this is expectation of Q1, the expectation of Q1 that we need there. So bringing all the pieces together, you obtain this equation, again, a linear equation in the expectation of Q1 that you can solve with a fairly bit of algebra, and you obtain that the expectation of Q1 is 1 over lambda plus mu over lambda squared. Okay, so you have the expectation of Q1, you have the expectation of Q0, because you obtain there your expectation of t, which is 1 over lambda plus, this 1 over lambda, that's 2 over lambda, plus mu over lambda squared. Okay, that's the final answer. Okay. Yeah, so a longer question, but doesn't really take you by surprise, because if you look in the tutorial question, that's in fact exactly the tutorial question 6.27. So if you are familiar with the tutorial questions and you have full solutions to those questions, that's something that you should have seen before. All right, so you should be able to do that. Okay, part B. In the long run, what proportion of time is there at least one machine working? Well, again, in the long term, what is the probability that you will see this or that happening? We are talking here about the stationary distribution. So it's about obtaining that stationary distribution. We are in a very simple case, okay, of a birth and death process. So part B, in the long run, what proportion of time is there at least one machine working? Well, in the long run, what's the probability of this or that happening? Of course, we are talking here about the stationary distribution of the chain. We are here in a very simple case of a birth and death process, and we know that for the birth and death process, the balance equations, like basically the equation you should solve for obtaining the stationary distribution, takes a simple form known as the local balance equations, which is basically that if you just build a wall here, the virtual wall, what you are saying is that everything which moves from here to there, from the right hand side of the wall to the left hand side of the wall, should go back basically, so that must be equal to everything which moves from the left hand side of the wall to the right hand side of the wall. So here that means, for that wall in particular, we say that pi 0 times lambda, so pi 0 times lambda, that's basically the flow that will move from the left to the right. That's the proportion of time will be in state 0 times the rate out of there, across that wall. That must be equal to this flow, and this flow is the time you've spent in state 1 times the rate at which from state 1 you will move to state 0, which is mu. Okay, and you build a second wall here, and you say that again everything which moves from here to there must be equal to what moves from there over to here. That's pi 1 times lambda, the fraction of time you spend here times the rate at which you will effectively make that transition must be equal to the fraction of time you spend here, pi 2, times the rate at which you will effectively make that jump back to state 1, pi 2, times mu. And then you can just solve these equations. It's very simple in that case, okay? You obtain from here that pi 1 is pi over mu pi 0, sorry, lambda over mu pi 0, and here you obtain that pi 2 is lambda over mu pi 1, which happens to be lambda over mu squared times pi 0. Okay, you ask for the sum to be equal to 1, everything here pi 1 and pi 2 are just constants times pi 0, 1 plus lambda over mu plus lambda over mu squared must be equal to 1, of which you obtain that pi 0 is 1 over this block here. And if you want a nicer version of it, I'm not sure it's really nicer, but still, mu squared plus lambda mu plus lambda squared is pi 0. Pi 1, well, you multiply this expression by just lambda over mu. One of the factor mu here will go, replaced by a factor lambda, basically that's the only difference. So that's lambda mu squared plus lambda mu plus lambda squared. And I could obtain, of course, pi 2 the same way, multiplying this again by lambda over mu, lambda squared over the denominator. But in fact, you don't really need it, Again, the question is just about the proportion of time, as it is stated there, that at least one machine is working. Because I define my chain here as the number of machines down, at least one machine working. That means that we should be either in state 0, no machines down, the two are working, or in state 1, one machine down, one machine working. You cannot be there because in that situation, no machine is working. So it's just pi 0 plus pi 1, actually. So it's enough to have these two expressions. The final answer would be the sum of these two things. All right, now, as promised, I will have a look back at question 4 for 3901. It's only worth 5 marks, so basically it's a short question, a bit like a bonus question. I just ask you to show me the generator matrix of a certain chain, which is kind of, as per the question, kind of an M1 queuing system, but with a slight variation. And I just basically ask you to tell me how you would attack or you would model that situation, okay? Just as I said, 5 marks, just if you can tell me that, I would be happy and I give you 5 marks. If not, you know, that wouldn't make a huge difference, I suppose, in terms of your final marks. So that's the idea. So indeed, you have that MM1 queuing system with service rate mu, as usual, but assume that the customers arrive in batches, meaning that each time you have an arrival, let's say, in the initial process, it's not only one customer which arrive, but that can be either 1, or maybe 2, or maybe 3, or maybe more. In fact, the customers, they join the system in batches, or in groups of people, basically. And we are told that the batches arrive according to a Poisson process with rate lambda, so really the arrivals of the batches, that's the usual thing, according to a Poisson process, okay? But each arrival delivers a batch of customers, the batch size being distributed as a random variable n with the probability that n is equal to n is Pn. Okay? So, in fact, it's not really specified what it is. We are just saying that the number of people in a given batch will be equal to a certain n with a certain probability Pn. N can be 1 or 2 or 3 or more. There is no real limits on that apparently. And of course, if you sum all these values Pn, you must find one, cover all the possibilities. Okay? Find the generator matrix of this chain. So let's see what we have. So you have your initial MM1 queuing system. The only thing is that each time you see one arrival in that initial MM1 queuing system, it's not always 1 people who joins the system, but sometimes 2, sometimes 3, sometimes 4, according to this probability distribution. Okay, so basically what you have the process of the arrivals of the batches. And by definition, this follows a Poisson process with rate lambda. Okay? But if you look at that this way, you say batches with 1 customer. What is that? You can really just spot the groups of people, but made up of only 1 person. So it's not a real group in that situation, but still, out of all the batches which arrive, you just focus on the batches which are just made up of 1 person. Okay? This is this. Basically what you do, you split the initial Poisson process into sub-processes. In that situation, you know, you have the arrival type 1, arrival of type 2, and so on. And you know that if you split a Poisson process into sub-processes that way, what you create is sub-processes which are also Poisson processes, with rates being equal to the initial rate times the probability of being that type of arrival. Here, the probability that one batch is actually made up of only 1 customer is P1. So in fact, those things they arrive according to a Poisson process with rate lambda times P1. And the rest follow. If you just focus on, let's say, the batches with 2 customers, this arrives with, according to a Poisson process, with rate lambda times P2. Okay? Each of these arrivals here, they are divided into the batches consisting of 2 people with rate P2 and the others. So that particular branch that you create as a sub-process of this one is also a Poisson process with rate lambda times P2. And more generally, you have batches consisting of n customers they arrive according to a Poisson process just with rate lambda times Pn. Okay. What happens concretely on the chain when this happens? The chain jump to a state +1. You are in a current state, there are a certain number of customers right now. If this happens, then the chain will move to the next state, just +1 customer, as usual in that situation. If this happens, 2 customers join the chain. So the chain will just move to a state +2. Okay, you have a certain number of customers right now, a batch of 2 people arrive, automatically the number of customers in the chain jump to that current number +2, yes. And if you have, of course, batch of n customers, in terms of the chain, it moves to a state +n, okay? Let's draw a diagram of that chain. You are in state 0, state 1, state 2, state 3, and so on. The chain here, currently in state 0, will jump to state 1 with a rate which is an exponential rate of rate lambda P1. The chain will jump to state 2 directly if the next batch which is arriving is made up of 2 people. So that happens with an exponential rate because Poisson process. Lambda P2. From 0 you can jump directly to state 3 with a rate lambda P3, and basically you can be sent to any of those higher states with a certain probability. Okay. If you're in state 1, same thing, you can move to the next state if the next batch that you see is made up of just 1 people with rate lambda P1. 2 people, in such a case you will move to state 3, lambda P2. 3 people, and maybe more. From state 2, you move to the next state with rate lambda P1, and so on and so on. And you see what it gets. Of course, I cannot draw everything there because that would get a bit messy very soon, but that's it. What about the service rates? That means here the departure rates. In terms of the departure, that's the usual thing because we are effectively in an N-1 system. So that means there is 1 server serving 1 person at a time. Even if people join in batches, still they are served 1 at a time. So the service rate is mu everywhere. Okay, if you have 3 people in the chain right now, that doesn't matter. 1 at a time is being served, and so 1 will leave the system at an exponential rate mu. Okay. And so this is roughly the chain that we have. And the question is about what's the generator matrix of that chain? Well, once you have sketched that, just about writing those things into a matrix. Okay. G. From state 0, you can go to state 1 with rate lambda P1, to state 2 with rate lambda P2, lambda P3, and so on, up to infinity, basically. Here you have the negative of the global rate out of state 0, so basically that's the sum of all those things, or the negative of the sum of all those things. But we know that altogether the values P1, P2, P3, they sum to 1 by definition. So when you take the sum of all those things, that must be equal to lambda. The global rate out of state 0 is just lambda, of course. And yeah, that makes sense. You will leave state 0 if you see one batch arriving. One batch, whatever its size, basically. If you see one batch arriving, you would see some customers joining the system, so you would leave state 0. Okay? And of course, the batches, they arrive according to a Poisson process with rate lambda, so the rate of this is lambda. From there, same thing, you have everywhere minus lambda plus mu on the diagonal, lambda p1, lambda p2, lambda p3, and so on. Minus lambda plus mu, lambda p1, lambda p2, and so on. Why lambda plus mu here? Well, because the lambda out of state 1, that's all those transitions towards the higher states when you see batches arriving. But of course, from state 1, you can also leave it back to state 0 with a rate mu. So in fact, you have a mu here. Okay, so the global rate out of state 1, that's those things altogether lambda, but plus that mu here. Okay, and same thing here. From state 2, you can move back to state 1, this mu, or move to the higher states, all those lambda p something. Altogether, this is lambda, this is mu, so the rate out of state 2, the global rate is minus lambda plus mu, 0. You cannot move from state 2 to state 0. And on the sub-diagonal here, you have all mu's. On the main diagonals here, you have all, correct, that should be something like this, minus lambda plus mu's, and here on this diagonal, lambda p1, lambda p2, and so on. Right? So I would take anything which vaguely looks like something like that, if you make it clear what the structure of the matrix would be. So this question was roughly about queuing theory. So let's move to question 5 for 3801, which is also about queuing theory. Consider a first in, first out MM1 queue with customer arrival rate lambda and a service rate mu. Classical situation, very simple situation. The system is empty. There is no customer in the queue or in service at time t equal to 0. So that's the opening of the post office, let's say. So nobody in the system at time t0. The first customer to join the queue can thus enter service upon arrival, but the second customer may have to wait if the server is busy. Find the expected total time spent in the system, the total time spent in the system, so waiting time plus service time for the second customer. All right, so what we have is something like this. That's the counter. Time t equal to 0, nobody's there. Then opening. One customer enters service directly because the system is empty. So at the time it joins, you can really enter service straight away. And then you have a second customer joining. Okay? And that's the one we are interested in. We want to know what is the total time spent in the system by that guy. The total time spent in the system, t, is, as made it clear in the question, the waiting time plus the service time. Okay? And again, we want the average total time. So take the expectation of this. That's the expectation of that plus the expectation of this. Okay? For the service time, it's very easy. Because we are in a MM1 queuing system, MM1, M means that the service time is Markovian, meaning that it's exponentially distributed. So S, the service provided by the counter here happens at an exponential rate mu. Okay. So basically, the expectation of S is just 1 over mu, as usual. So that bit here, okay, we've got it, easy. Once that second customer enters service, the service time is exponential. On average, that will be 1 over mu. More complicated is to obtain this expected waiting time. Why is that more complicated? Because, in fact, two different things can occur. Imagine that at the time of that second customer joining the system, the first customer is done with service. So it's been, he has left already. Okay, so that may be the case, you know. There is a first customer arriving, getting service, is done with service, is leaving. And then after that only, a second customer arrives. That second customer finds the system totally empty. He can enter service straight away as well. And the waiting time in that situation, 0. He doesn't have to wait. Or, no. The first customer is still there at the time at which this one enters the post office. Why not? Okay, you have a first customer getting service, and during the time that is being served, there is that second customer joining the system. In such a situation, that guy has to wait. Okay, so one situation, no waiting. A second situation, some waiting. Two different scenarios, two different situations, leading to different expressions for the waiting time. Okay, let's split that waiting time into what would happen under the first scenario, what would happen under the second scenario. You know how to do that. Let's condition. Right? So in fact, the expectation of W, you can say by the law of total probability, the law of iterated expectations, that's the same kind of thing, that it's the expectation of W if there is any waiting times the probability that there is any waiting plus the expectation of W if there is no waiting at all, that's the probability that there is no waiting at all. Okay? Okay, that's easy, that one. What's the probability, what's the expectation of W if there is no waiting? I'm telling you, there is no waiting. All right? So W is equal to 0, so that's 0. And I don't really have to care about that one. Okay? So the only thing I have to find is this probability and this expectation, and that's it. Okay, okay, let's do that. Expectation, let's start with that one. Probability of any waiting. What is the chance that that guy has to wait when he arrives? When I say that, that will happen if the first customer here is still being served at the time of arrival of that second customer. Okay? So that's the probability that actually the service time of the first customer, let's denote it S1, but that S1, that's the same as the service time for any customer. I'm just writing S1 to make it clear that I'm talking here about the first customer. That service time must be longer than the time that we have between the two arrivals, the arrival of the first customer and the arrival of the second customer. That time between two successive arrivals, that's what we call the inter-arrival time. That's x2, because we are talking here about the Poisson process. The customers join in an NM1 system according to a Poisson process. So the time between the first arrival and the second arrival, that's in fact the second inter-arrival time, denoted x2 within the framework of Poisson processes. Okay? So, indeed, if the time between the two arrivals is shorter than the service time, then the time that guy joined, he will still find the first customer in service and he will have to wait. Okay? If x2 is longer than s1, at the time the second customer joined the system, the service time of the first one, it's over and the first customer is left and no waiting. So this is really the probability that we're after. What's the probability that s1 is longer than x2? Can I do that? Yes, again, this is exponentially distributed. The inter-arrival time between two customers in the Poisson process is exponentially distributed with rate lambda. I'm assuming in an NM1 system, that's one of the working assumptions, that all the times are independent. In fact, that's one of the assumptions in a continuous time Markov chain, more generally. So x here is independent of s. This x2 is independent of s1. Again, I have to pick what's the probability that one of two independent exponential random variables is that one in particular. And I said that's the ratio of the rate of the smallest one to the sum of all the rates, basically, which is just here lambda plus mu. So the probability that they will have to wait is just this ratio here. Okay. So that's what we have. Now, second step. Given that there is some weighting, what is the expectation of W? Okay. Well, W in that situation would be just, well, precisely the second customer joins the system. The time we have to wait is the remaining service time of the first customer. So basically that's the expectation of, let's write it this way, remaining service time, okay, of the first customer. But the nice thing is that that service time is exponential, it's memoryless by definition. So the remaining service time is basically also exponentially distributed with the same parameter. The distribution of the remaining service time is the initial distribution, memoryless property of the exponential distribution. So in fact, on average, the remaining service time is just 1 over mu. I of course don't need that expectation here. Okay. So in fact, yeah, that's the expectation of S. That's 1 over mu. Okay, by the memoryless property of that exponential distribution. Okay, so if that guy has to wait, on average, you would have to wait 1 over mu minutes inside. Otherwise, you don't have to wait. Right. So we have now all the pieces where you need. You can obtain by this that the expectation of W is this 1 over mu times lambda plus mu. Okay, that's the expected waiting time, and S, it's 1 over mu. Okay, meaning that altogether the total time spent in the system is just 1 over mu 1 plus lambda plus mu. Alright, so let's now look at question 6 for 3901, also within the framework of queuing system kind of things, but it's more like about, you know, continuous time, Markov chains and those things. Consider an NM2 queuing system with heterogeneous servers. That's the slight complication that I prompted in that question. Yeah, an NM2 basic queuing system, all the servers are providing service at the same rate. But it need not be the case, and I said it, I think, when I introduced those queuing systems. I said if you have a multi-server system, not all of them are forced to provide service at the same rate. You may have more experienced employees at the checkout counters, for instance, serving the customers quicker than others, for instance. Okay, that may be the case. And here, this is what we have. The exponential arrival rate is lambda, as usual, but the server 1 and server 2 have different exponential service rates, theta 1 larger than theta 2. So theta 1 larger than theta 2, that means that the service rate at server 1 is quicker. The rate is higher, so the people leave the system quicker if they are served at server 1. So that means that indeed the service rate is shorter. Okay, the service time is shorter, and the rate is higher. If server 1 becomes idle, then the customer being served by server 2 instantaneously switched to server 1. So precisely because server 1 is quicker, server 2 will be used only if need be. So if there is somebody being served by server 1 right now, a new joining customer will enter service with server 2. But as soon as server 1 becomes available, that person being served at server 2 will switch to server 1 to enjoy the quicker service rate, basically. Okay? So in fact, server 2 can never be busy while server 1 is idle. No, it's not possible. Okay? So server 1 is always the priority. All the customers will be directed to server 1 if free. If not, then they can enter service with server 2, if that makes sense. All right? So basically, the chain is something like this. 0, 1, 2, 3, and so on. The usual, MM1 or MM2 in that queuing system, so it's like a birth and death process. People join the system with rate lambda, as usual. Okay. And if there is one person in the system, that guy is being served by server 1. So from state 1, we will leave and go back to state 0 with a rate which is theta 1, which is the service rate at server 1. One person is being served by server 1. It would leave the system with that rate. If now we have two people in the system, one is being served by server 1, the other one is being served by server 2, that means that the total service rate and the rate at which we will see any one of the two leaving is just the sum of the two rates, lambda 1 plus, theta 1 plus theta 2. And in fact, for the higher state, that's the same thing. Suppose there are three people in the system, only two can be served at the same time, one by server 1, one by server 2, the third one would be queuing. And the other customers would be queuing as well. So all the def rates from that point on, they will all be equal to just theta 1 plus theta 2. Okay? So give the birth and death rates for the system. Well, of course, that's the rates which appear here on this diagram. All right? B, find the condition for the queue to be stable. So we know that for a queuing system, we say that the queue is stable if it remains finite in length. And for some system, if precisely the service rate is not able to cope with all the arrivals, the queue length will become infinite. Basically, the system will explode. Okay, if you are not able to cope with the demand, basically, the queue length will just grow indefinitely, and we'll see more and more and more people joining the queue without being able to serve all of them, and the system explodes. The system is said to be unstable. So what's the condition for the queue to be stable in that situation? And I said, okay, it's easy, intuitively to understand. The service rates here for the highest states must be bigger than the arrival rates for those higher states. What really happens here in the beginning of the chain, that doesn't matter much, If you cannot manage to cope with this demand here in this area, that doesn't matter much. If you manage to cope with the demand here for the higher state, you would keep the chain basically in the acceptable area. You don't allow the chain to go too far away towards the higher value. So that's the idea. And, it's a birth and death process, clearly, you have the structure with the birth rates and the death rates that you have identified by now. So we know that the condition for stability is to have this. And you can check in your lecture notes that indeed that's the case. This big sum here, which is the sum of the ratios, the product of the first k birth rates to the first k death rates, must be finite. Okay, that's the condition for the chain to admit a stationary distribution. And I explained there that if the chain admits a stationary distribution, that means that we have the control of the chain here in this area. That means that the length of the queue is under control. That means that the system is stable. Okay? So in fact, we have to check this condition. But here we have that particular structure, which makes quite easy to check this condition. So that must be here in that situation. Sum for k between 1 and infinity. all those lambdas, they are all equal. So it's just lambda to the power k. You have k factors here. Okay? And here, well, pretty much all of them are equal to lambda 1 plus lambda 2. Not all of them, because the first one, mu1, and mu1 it will always be there, is just equal to theta 1. So in fact, you have here theta 1 plus theta 2 to the power k minus 1 times theta 1, which is the last mu1 there. Okay? So in fact, you want this to be finite. Well, as it is right now, well, it is what it is, but you can in fact write a simple version of it, because what really annoys you is that you don't have the same power here as there, and you have that coefficient theta 1 here that basically doesn't matter much. It doesn't depend on k. That's not about this, that the convergence of the series will be achieved or not. So let's write it outside, and let's take one of these factors outside too. So let's write theta 1 plus theta 2 over theta 1 sum, okay, lambda to the power k. Here, because I have written one factor here, I need one more there. Theta 1 plus theta 2 to the power k. And this theta 1 is the one which is there. That's equal. And then you can see that indeed the criterion that you need for this sum to converge is a very classical result, and I use that result many times in class, and also I suppose in the tutorial questions you've seen that, so you should know that. This thing here should be smaller than 1 in absolute value, but here everything is positive, so I don't really need the absolute value. So this must be smaller than 1. And this is what you need basically. And again, we can understand that. I said what really happens here at the beginning of the chain, like close to the state 0, doesn't matter much. So theta 1 alone here, does it manage to cope with lambda? We don't really care. What is important is what happens here towards the higher state, and we can see that indeed you will manage to cope with the diamond if clearly theta 1 plus theta 2 is larger than lambda, and of course this is what this condition asks you, right? So for part C, under the above condition, so assuming that lambda is smaller than theta 1 plus theta 2, what is the stationary distribution of the system? Again, it's quite easy because we are here in a birth and death process situation. And we have explicit expression for the stationary distribution of such a birth and death process. In particular, I can tell you directly that pi 0 must be 1 over 1 plus this whole thing. Okay? This is what you would find in the lecture notes, right? Okay, this is the expression. So you don't really have to like re-derive those expressions from scratch. I would be very happy if you use directly this expression, saying, okay, I am in a birth and death process. The stationary distribution in that situation is this one. The value pi 0 is this one. Okay. So basically, as you can say, that's the same thing as that. Yes, it must be. And I wrote it before in part B. Theta 1 plus theta 2 over theta 1, sum for k between 1 and infinity, lambda over theta 1 plus theta 2 to the power k minus 1. And we know that this, again, you have the sum of all the powers of something smaller than 1, that's why we need this condition. We know what it is. 1 over 1 minus x is the sum for k between 0 and infinity of x to the power k. Here the sum doesn't start at 0, but it starts at 1. So you have to play a bit with that, basically. But still, if you do it, I skip the details, right? You would obtain a final expression for your pi 0, something nice like theta 1 plus theta 2 minus lambda divided by theta 1 plus theta 2 plus theta 2 over theta 1 times lambda. That's your pi 0. And your pi j, for any j bigger than 0. Again, you can just use like the expressions that are well known for birth and death process. Basically, you stop at the jth term here. Okay, so you have the thing which is here, but you stop at the jth element for pi j. All right? Times pi 0. Okay. So in fact, given that this is just lambda to the power j, this is theta 1 plus theta 2 to the power j minus 1 times basically the thing that you have there. And eventually you can try to simplify this expression. Anyway. All right, and so last question for 3801, it's question 6. It's about the Brownian motion. Part A, consider a Brownian motion, standard Brownian motion like this. Show that for s smaller than t, bs minus s over t bt and bt, this is a block, and bt are independent. So basically what we have, imagine you have a Brownian motion here, started from time 0 in 0, as a Brownian motion should do, sorry. You have a red thing like that, and at time t, let's say here, you are in this position bt. What is exactly this bs minus s over t bt? So you fix the time s, I don't know, this one here. Bs, apparently in my situation, was up there. And in fact, s over t times bt, again, it's just a linear approximation of your location. So you go from 0 to bt at time s. According to the straight line, you would be exactly at this location. So this is what you do. You have this straight line here. So roughly you would expect, knowing that you end up in bt there, you would expect the Brownian motion to be there at time s. Of course, it's never there. It's just an estimation, somehow, an approximation. It happened that you were actually up there in my situation. So this is actually the difference between where you were effectively at time s and what you thought you would be. All right? So this is basically this blue distance. Okay? And this one, dt, is this red distance. The question is about showing that this blue quantity, random, because it's all about the Brownian motion, which is random, and that red quantity, random as well, they are independent. If I tell you this value, that doesn't tell you anything about that value and vice versa. How would you do that? Well, I suggest to first compute the covariance between the two things. So let's see if we can obtain a covariance between this and that. So bs minus s over t bt and bt. It's covariance of a sum. So I know that I can write it as the sum of the covariances, each term here with bt. So that's the covariance of bs with bt, plus, in theory, the covariance of this Boole block minus s over t bt with bt, but minus s over t is a constant. I know that I can also write it outside of the covariance. So minus s over t, covariance bt with bt. Okay. This one is easy because the covariance of a random variable with itself is just the variance. So that's the variance of bt. And this one, that's the covariance of bs with bt. But we do know the covariance function of the Brownian motion. It happens to be the minimum between the two times s and t. It's something that we showed in class. All right. So this covariance function of the Brownian motion between what happens at two distinct times It's just the minimum between the two times. Okay? So everything minimum between S and T minus S over T times this variance. The minimum between S and T, we are told here that S is smaller than T. Yeah, it's all about that. It's all about being before that. In the future, I don't know exactly what's going to happen. So S smaller than T means that this minimum is S minus S over T times variance of BT, but that's the variance of the Brownian motion at time T. By definition, BT follows the normal distribution with mean 0 and variance T. That's the definition. Variance of BT is just T. And what you see is that T and T, there you go, S minus S. That's 0. So the covariance is 0. Is that enough to show that they are actually independent? No. We know that two not correlated random variables are not necessarily independent. Okay? Not correlated means no linear link. You cannot draw a nice straight line if you plot a scatter plot of the two random variables. Okay? But there may be another kind of link, like a quadratic link or something more complex as a dependent structure. Something much more complex than just a linear link. All right? So not correlated doesn't mean they are independent. So in fact, just seeing this is not enough for concluding about the independence or not of the two quantities there. It turns out that in this situation, that's the case because we have in a very particular case of random variables which are normally distributed. And that's the only case in which no correlation implies independence. Again, we said that in class. If the random variables that we have are normal, in particular if they form a bivariate normal vector, then seeing that there is essentially no correlation between them implies that they are actually independent. Are those things normally distributed? Yes, I just said it. BT, by definition, follows the normal distribution for all t with mean 0 and variance t. BS, by definition, is also normally distributed. This is normally distributed, so I have a linear combination of normally distributed random variables. In fact, they do form these things a multivariate, well, a bivariate normal distribution, meaning that any linear combination of them is also normally distributed. Okay, so clearly this is normal, this is normal. If we see that their covariance is equal to 0, that means that they are independent. And that allows you to conclude that they are independent. But I repeat, for full marks on this question, this is not enough. You should, I will not write it here because that would be long, just words basically, but you should make it clear that you can conclude they are independent because they have covariance equal to 0 and they are basically elements of a bivariate normal random vector. Okay. Yeah, there is a part B, by the way, in a bicycle race between two competitors, but you should recognize this question. In fact, that part B is just example 10.1, sorry, in the lecture notes, and that's an example on which I spent some time in class in week 12, so I will not re-explain it explicitly right now, basically, because I did it in class already. All right, and finally, question 7 for 3901, it's again about the Brownian motion. So part A, let ZU be the Brownian bridge process. Okay, so you have a process that I call ZU, U between 0 and 1. We know that this is where the Brownian bridge process is defined. So precisely, it's the Brownian bridge. Okay, we know what it means. Okay, what it means is that ZU at any times is normally distributed. The expectation of U is 0 for all U, and the covariance we'll not use T here, let's say U1 and U2, for the Brownian bridge happens to be U1 1 minus U2 for U1 smaller than U2. Okay, that's the characteristics of the Brownian bridge process. So it's a Gaussian process. Okay? So knowing its mean function and its covariance function is enough for fully characterizing the Brownian bridge process. So here is the mean function, 0 everywhere. The covariance function, what happens at two distinct times. If u1 is smaller than u2, the covariance is given by this function. That's something that we explained in class. Okay. That's the Brownian bridge. Now, show that if you define another process, yt t plus 1 z t over t plus 1, the process yt that I define this way, so that's my Brownian bridge, all right? But the process t that I define this way is the Brownian motion process. How would you prove that a given process is a Brownian motion process? I just say there, a Gaussian process, it's easy because it's univocally defined by its mean function and its covariance function. Okay? Of course, the Brownian motion is a Gaussian process. So if I manage to show that this process here, defined through this equation, has for mean function the mean function of the Gaussian process known as the Brownian motion, and the covariance function equal to the covariance function of the Gaussian process known as the Brownian motion, that's it. So let's see what we have. For yt, well, first thing I have to show that it's a Gaussian process. Is yt normally distributed? Basically, that's the question. It's just a rescale version. You multiply that thing by t plus 1. So this is just a constant times z. Z, for any u, it's normally distributed. So that u, you can take it as t over t plus 1. T over t plus 1, that's something between 0 and 1, so this is well defined. For that u, you have a normal distribution. So you take here a normal distribution, you multiply it by a constant, that remains a normal distribution. So of course, this yt is normally distributed for any time t. So this is a Gaussian process. So indeed, I will be able to conclude just by looking at the mean and the covariance function. What is the mean function? Well, expectation of this, t plus 1, expectation of z at time t over t plus 1. Z at any time u has expectation 0, so if that u happens to be t over t plus 1, that's fine, but the expectation here is 0. So in fact, this process has mean function, again, 0 everywhere. And that's a good thing if we want to show this, because we know that the mean function of the Brownian motion is also flat 0 everywhere. So for the mean function, okay, let's see for the covariance function. Covariance, let's take S and T, and I will take S smaller than T. Okay. So, by definition, this is the covariance of, you redefine Ys according to this equation. S plus 1, Z, S over S plus 1. Yt, well, that's given there. All right. Constant, write it in front. Covariance between Z at time S plus 1 and Z at time T over T plus 1. So that's a covariance function for the Brownian bridge. My Z here, that's my Brownian bridge. We know the covariance function of the Brownian bridge. That's this one. If U1 is smaller than U2, here you have the covariance between what happens at time S over S plus 1 and T over T plus 1. But it turns out that S over S plus 1 or T over T plus 1, they are increasing function. Okay? So basically, that's a function like this. Okay? From 0. It starts from 0, that it increases like this, and it tends to 1. Okay? T over T plus 1. Meaning that, in fact, S over S plus 1 will be smaller than T over T plus 1 if S is smaller than T. And that's the case because this is what I am assuming here. S is smaller than t, meaning that this is smaller than that. So you can see this as your u1 in that expression, and you can see this as your u2 in that expression, meaning that you have at the end s plus 1 t plus 1 times the covariance which is given there, u1, that's s over s plus 1, times 1 minus u2, 1 minus t over t plus 1. Okay, and you can see that s plus 1, that will go, and you will see also that you obtain here t plus 1 times s time 1 over t plus 1. Okay, this is 1 over t plus 1. So that goes 2, and it just remains s. So the covariance function for that process y between ys and yt, if s is smaller than t, that's just s. Switch around s and t, we can conclude that the covariance between ys and yt, without fixing which one is smaller, is just the minimum between s and t, and this, I suppose, you can recognize the covariance function that we gave for the Brownian motion. Okay. So I have y, a Gaussian process with mean equal to 0, the mean function of the Brownian motion, with covariance function equal to this, the covariance function of the Brownian motion. Altogether, that process must be a Brownian motion process. There is no other choice. Okay? So that's it. This is how you prove that. Part B, again, that's example 6.10.1 that I talked about in class. I will not do it again explicitly right now. All right, so I will leave it there. I wish you all the best for the exam, and maybe see you later.